Hi everyone, welcome to another LIC class. In the previous class, we spoke about slew rate and the effects of slew rate on the frequency response. I've also posted the first homework. The first homework would be the question that you had at the end of the previous lecture for practice problems, which are on slew rates and gains. And you would have until the 18th to turn in the homework. If you have any questions about the homework, just please let me know. So this week, we're gonna speak about ideal op amps, the characteristics of an ideal op amp, and different operations of an ideal op amp. So we previously learned for an op amp, we usually have 5 terminals. We have the inverting input, we have the non-inverting input, we have the power supplies, positive power supply and negative power supply, and we have 1 output. So 2 signal inputs, the inverting and the non-inverting, positive power supply and the output. The op amp could be used for both AC or DC signals. So the inverting and non-inverting input could, we can give both AC signals or DC signals to the inputs. We have 3 packagings, as mentioned, metal can and dual inline and flat package. We learned about the internal components of an op amp, different stages of amplifier transistors. Now we want to learn a little bit about a simplified model of an op amp. We can model a op amp, a multi-stage op amp with a simple resistive input network and a voltage source output. The output source is a dependent source, and it's a voltage controlled voltage source. And the value of the source, the output voltage, would be AV, or the total gain, times Vn plus minus Vn negative. So this is just a modeling of what we already know. So the input network is specified as a resistance from each input to the ground, as well as an input to input isolation resistor. You can see that each has a resistor connected to it to the ground, and also it's connected, it's isolated between the resistors as well, between the inputs with the resistor as well. As we learned previously, the input resistance for an op amp is pretty high, around 300 kilo ohms at lower frequencies. For an op amp, the output is the product of the gain times the gain with the difference between the inverting and non-inverting input. That gain is usually pretty high. And the output impedance is pretty low in an op amp. Now let's speak about some specifications of an ideal op amp. So the desirable characteristics from an ideal operational amplifiers are: 1, the open loop voltage gain should be very high, ideally infinite. We already spoke about this. This is a quick review. of the table. Do you remember we had a table comparing ideal op amp with the practical op amp? The input resistance should be very high, ideally infinite. The output resistance should be very low, ideally 0. Full power bandwidth should be as wide as possible. Slew rate should be as large as possible, and input offset should be as small as possible. And we also had this table. This is just a review of the previous class, comparing an ideal with a real world op amp. So the properties, let's dive into the properties of an ideal op amp. The first property is that an ideal op amp has an infinite open loop gain. So AV in an op amp would be infinite. Therefore, V out in a system is AV times V positive minus V negative, or V in positive minus V in negative. So if AV is infinite, V out would also be infinite. So if V out is infinite, and we have an ideal op amp, then what happens is if I give it a 1 volt input, I would have infinite at the output. So I can power a city like Amarillo with a AA battery, but that's not actually how it works. The output voltage is limited to the power supply, how much of power supply I can give to the system. In the ideal op amp, as mentioned, it's infinite, but typically the value is between 20,000 and 200,000, which is a pretty large number again. And as we know, an open loop is a gain without any feedback. The next thing is that the ideal op amp has an infinite input impedance. And the input impedance is the ratio of the input voltage to the input current. So according to the Ohm's law, we already know that V is equal to Ri, or Z is equal to V in over In. So this, if I change this to find In would be equal to V in over the input impedance, yes? So if the input impedance is infinite, what would In be? And we have a constant voltage, like a 3 volt or something like that. It would be 0. Anything divided by infinite would be 0. Therefore, the input current, and this is very important, the input current in a ideal op amp is always equal to 0. Usually in a high grade op amp, the input resistance is in the range of tera ohms, which is very high. But some lower grades have mega ohm resistors and milliamp input currents. But for an ideal op amp, the input current should be equal to 0. Property number 3, we have 0 output impedance. Again, output impedance would be the ratio of the output voltage over its current. And it should be ideally 0, but it's usually in the range of 20 to 100 ohms. This internal resistance is in series with the load reducing the output voltage available to the load. Property number 4, 0 noise contribution, meaning that the op amp, an ideal op amp, should not add any noise to the system on its own. But in reality, the power supply and the internal components of an op amp, they add noise. We have thermal noise, we have electromagnetic noise, and so on. It's going to be added to the system eventually. But But in an ideal op-amp, we assume that there is zero noise voltage produced internally. But a practical op-amp is affected again by several noises, such as resistive and semiconductor noise. These effects can have considerable effects in low signal level applications. Property number 5, we have zero output offset. The output offset is the output voltage of an amplifier when both inputs are grounded. We already learned that if you don't give an op-amp any input, you should get zero output, or if you give it an input of 0, you have to get an output of 0. But in a real world scenario, they have some amount of output offset voltage. And what we did in an op-amp, we have the DC offset voltage cancellation pins number 1 and 5 that I showed you, that you connected with a resistor to the power supply and cancel that offset voltage, DC offset voltage. And an ideal op-amp must have infinite bandwidth, meaning it should amplify signals from DC, which is 0 hertz, up to the highest AC frequency, ideally infinite. But in real world, they are very limited. And by the way, this limitation is called the gain bandwidth product. It means in which frequencies the amplifier operates, and that frequency is called the gain bandwidth product of the system, and which is equal to the frequency where the amplifier gain becomes unity. Some op-amps, such as the 741, have a very limited bandwidth frequency of a few kilohertz. I spoke about frequency response in the previous class as well. In the ideal op-amp, a voltage applied to one input. The next property is a differential input sticks together. In the ideal op-amp, a voltage applied to one input also appears at the other input. And this is very important as well. So in an ideal op-amp, always V positive is equal to V negative. We can say Vn positive is equal to Vn negative. So differential input stick together in an ideal op-amp, and this is very important. A voltage applied to one input also appears at the other input. So we have 3 basic operations of an op-amp using the properties that we learned. We have the inverting amplifier, non-inverting amplifier, and differential amplifier. So let's dive a little bit into operational amplifier circuits. And we're going to start with what we call an inverting amplifier. So 3 things to keep in mind, and these are very important. Again, I just want to. First, the gain is infinite. Second, the input resistance is infinite, therefore the input current is always 0. Third thing that you need to keep in mind is Vn positive is always equal to Vn negative. So these 3 things are the most important things that we have in an ideal op-amp. An ideal op-amp, this is a schematic for an ideal op-amp. Usually the negative input is connected to one voltage source, the positive could be connected to other, or we could simply ground one of the inputs. And the positive power supply is connected to the positive VCC. Negative power supply is connected to negative VCC. And you're going to see in the lab that the way that we connect these two is actually like this. We would have 2 power supplies for op-amp, and we would set one, for example, to 15 volts and the other one to 15 volts. We have to always keep them at the same value. And therefore, we connect the negative of one of them to the positive of the other, and that's going to be our common ground. And the positive will be connected to the positive end or the positive supply of the op amp, and the negative would be connected to the negative supply of the op amp. Now, what is the total voltage that I'm giving to this op amp? Perfect, 30 volts, because I have connected two 15 volts power supplies in series, and the voltage is between negative 15 and positive 15. We want to have a symmetrical, and I'll show you in the next slides, in the next classes, why we have this system. We can also have a single supply, but usually op amps, we use two power supplies. We connect them together to create a balanced positive negative supply for the system, so we can have a clean output signal as well. In an ideal operational amplifier, the slew rate, again, it's all, the slope is almost infinite, so you have a very large slew rate, and the output voltage is usually 1 to 2 volts less than the VCC, negative and positive VCC. Now let's start with some feedback. So first thing is that in 90% of the cases, we use an op amp with a feedback. We rarely use an op amp without a feedback unless we're going to use it as a competitor. And the reason is that because the op amp, the gain is so high, it makes the system unstable. And to make the system stable and to control the output, we always use a feedback. We can use a positive feedback or a negative feedback. So a negative feedback means that the output is connected to the inverting input or the negative input. A positive feedback would be the output connected to the positive input or the non-inverting input. So let's solve this. Let's go first with a inverting input or non-inverting input. Let's solve it for this one. So this particular amplifier is called a non-inverting amplifier. Okay. The reason that we call it a non-inverting amplifier is because the input is connected to the positive end. And if I give it a signal like this, the output would not have any phase shift. So you're going to have a little bit of gain, the system amplified, the signal amplified, but we don't have any phase shift, meaning if I give it a positive signal, I would have a positive in the output. If you give it a negative, you're going to have a negative in the output. So the system would not invert the signal. It's just going to keep the signal at the same phase. That's the reason we call it a non-inverting amplifier. So again, if in an amplifier, the input is connected to the positive input, is called a non-inverting amplifier. If it's connected to the negative, it's called the inverting amplifier. Now I want to find the gain of the system, or V out over V in. So the first thing I want to do is I'm going to use the principles that I had for an ideal op amp. And what were the principles? The first principle was that IN is equal to 0 and V in positive is equal to V in negative. So I'm going to use these two principles to find this equation, the results of this equation. Okay. So how can I find V out over here? Can you help me with this? How did you come up with that? Okay, and what is the relation between that and Vn? That's great, yeah. So let's start with this. First of all, we know that this current is equal to 0, yes? According to the first principle. And then we know that V negative is equal to V positive. Therefore, what is the voltage at this point? It's going to be Vn. Am I correct? Because V negative is equal to V positive, and what is V positive equal to? It's equal to Vn. Therefore, the voltage at this point is going to be Vn. Now, I can use the Kirchhoff's current law to be able to find V out in relation with Vn. So let's put it this way. I'm going to put a current coming in here, and I'm going to put a current coming here. Yes. And I'm going to call this node number 1. So for node number 1, I'm going to call this I1, and I'm going to call this I2. I1 plus I2 is equal to IN. Do you all agree? Yes, according to the Kirchhoff's current law. I1 plus I2 is equal to IN. And therefore, I1 plus I2 is equal to, what is IN? It's 0. Yes. Now, what is I1 equal to? What is I equal to according to the Ohm's law? Voltage over resistance. So if I want to find the current going through this resistor, and this is V positive and this is V negative, for example, or V negative and V positive, V negative, what is I going to be equal to? V negative minus V positive over R. Yes, am I correct? It's the difference between voltages. So this is going to be its voltage VR over R. Yes. So now here, what is the V negative? What is V positive? What is the output of this voltage? What is the output of I1? What is the end of I1? Vn, yes. So I1 would be Vn minus V out, or we can say V out minus Vn. It's not going to make any difference. Over R2. Am I correct? And what is I2 equal to? Using the same equation. It's going to be Vn minus 0, because here we have ground and the voltage here is equal to 0. Yes, it's ground. Over R1. Now let's put these two in that equation, I1 plus I2. So Vn minus V out over R2 plus Vn minus 0 over R1 is equal to 0. Am I correct? Yes. Add another. I don't know if I can solve it here. I have enough space or not. So the answer, let's go. Can I erase the one on the top? Is it okay if I erase this? Yes. So we use, I'm going to write that over here. We use the principle IN is equal to 0 and V positive is equal to V negative. So Vn minus V out over R2 plus Vn over R1 is equal to 0. We can multiply everything by R2. So we're going to have Vn minus V out plus R2 R1 over Vn. This is equal to 0. In other words, V out would be equal to Vn plus R2 over R1 Vn. Am I correct? Moving V out to the other side. So I'm going to factor out Vn. So V out would be 1 plus R2 over R1 Vn. Therefore, the gain AV would be 1 plus R2 over R1, or V out over Vn. And move Vn over here. So V out over Vn, or AV, is going to be 1 plus R2 over R. So for a non-inverting amplifier, AV, or the gain, would be V out over Vn, which is 1 plus R2 over R1. Now let's solve a few practice problems with this. So imagine I have two resistors connected to an non-inverting amplifier. Vn, this is ground. So Vn is equal to 3 volts. This is 1 kilo ohms. This is 6.8 kilo ohms. We want to calculate V out. What is V out? I'll give you a few minutes to think on this, and I'll. I'm going to go back to the equation that we had, if you want to write down, if you haven't already. So what is the answer? Did anyone find the answer?
3.4.
Yes, perfect. So V out would be 1 plus R2 over R1 times Vn, according to the equation. Therefore, V out would be equal to 1 plus 6.8 K over 1 K times 3 volts. So that's going to be 7.8 times 3 gives us 23.4 volts. Do you want me to solve another one, or I can move to the... Did you write it down? You want me to solve another one, or that's good? Okay. So the next one is, I'm going to give you some practice problems so you can do at home with these as well. So the next one that we have is called an inverting amplifier. So now, if the input is connected to the inverting or the negative input of an amplifier, it's called an inverting amplifier. Why do we call it an inverting amplifier? Because if we give it a signal like this, the output would have a 180-degree phase shift. So whenever this is positive, the input is positive, the output would be negative, and where the input is negative, the output would be positive. Because it's inverting the signal, it's called the inverting amplifier. Again, in an inverting amplifier, the input is connected to the inverting input or the negative input, or Vn negative. Now, let's find the gain AV for an inverting amplifier. So we want to find V out over Vn. Again, we're going to use the principles for an ideal op-amp. What are the principles or the operations? First one, the input current is equal to 0. Second one, V positive is equal to V negative. So input current, this current IN is equal to 0, and V positive is equal to V negative. Therefore, the voltage at this point, what is the voltage in this node? How much is the voltage at this node? Yes, perfect, because it's equal to this voltage, because these two voltages are equal. Therefore, the voltage in the negative input or the inverting input is always equal to 0, because the positive is connected to the ground 0 and negative and positive are equal. Again, we can use Kirchhoff's current law, and I'm going to call this again, I can call this I2, and I'm going to call this I1. So I1 plus I2 would be equal to the input current. Am I correct? And what is the input current? 0. Again, according to the Ohm's law, what is I1 equal to? So what is this equal to? It's V negative, V input negative, minus Vn over R1. And what is I2 equal to? Again, V negative minus V out over R2. What is V negative equal to? Vn negative 0, or we call it Va. So therefore, I1 plus I2 is going to be negative Vn over R1 plus negative V out over R2 is equal to 0. Am I correct? Yes. So V out over R2 would be equal to negative Vn over R1. Therefore, V out over Vn is going to be equal to negative R2 over R1, which is going to be equal to the gain. Or we can write it like this. V out would be equal to negative R2 over R1. Maybe write it up here. V out would be equal to negative R2 over R1 times Vn. Now let's solve a practice problem. This is 4.2. This is 2. Vn is 2 volts. This is connected to the ground. How much is V out? So Vn is 2 volts. R1 is 2 ohms. R2 is 4.2 ohms. I'm just going to go back to the equation. We had 4. So for a non-inverting amplifier, as I mentioned, so for an inverting amplifier, V out over Vn, this is the equation, is negative R2 over R, or AV. Our class is until 10:20, am I correct? Okay. So what is V out? So V out would be negative R2, which is negative 4.2, divided by 2 times the input voltage, which is 2 volts. So it's going to be 2.1, or we could just simply do this. It's going to be negative 4.2 volts. So as we can see, the input was a positive voltage, and now the output is a negative voltage. Since it's inverting the input, it's called an inverting amplifier. So the model for an inverting amplifier, if we want to show it, we can show it with a dependent voltage source, and the feedbacks R2 and R1 are also connected there. So I think it's enough for the course today. We're gonna have a quick quiz. Just want to mention this again. This is just a wrap up of the system. So summarizing the system, the input resistance of an op amp is infinite. therefore the input current is zero. This is important. And always the voltage difference between positive and negative are, there are no difference between the positive and negative input voltage, therefore the V positive is V equal to V negative. This applies to any system with a negative feedback. So any system that you have an ideal op amp, just using these two principles, IN is equal to zero and V positive is equal to V negative, you can solve them. And I'll explain about other applications of op amps as well. So let's see, let me see if I can pull out a code quiz real quick. Let me bring up another one, just give me a second. We already solved that one, didn't we? If the input voltage is 20 volts, I think that was the previous time, quiz number 3, so. Let's solve this one. Let's see if someone can solve. For the online students, I already uploaded their quiz. Their quiz would be online on their Blackboard. But I already shared this so they would get familiar with the in-class student quiz as well. Did you all join? 1, 2, 3. Okay. We want to determine the output voltage of the following circuit. You have 3 minutes. Again, remember the two principles that we had. Number one, the input current inside the op amp is always equal to 0. And number two, the inverting input and the non-inverting input are always equal. Okay, so the correct answer is -10. It's the same way exactly that I solved the previous question. We had I1 plus I2 is equal to IN. Here, I1 is already given, it's 1 milliamp, so it's gonna be 1 plus I2, and I2 is gonna be V out minus V negative, which here is again 0, so V out over 10K plus 1 gives us, and then it's gonna be negative V out over 10 is equal to 1, therefore V out would be -10. Let's see who got it right. Okay. I think we are out of time. Thank you, and I will see you on Thursday. I'm sorry? No, from next week, yeah. When we reach a certain point, we finish with the